Welcome to the first lecture of the first method section of the Industrial Ecology Open Online course. Industrial ecology is all about studying material and energy flows in industrial system, so the first thing we have to do is to learn about the basic concepts, definition and methodology of material and energy flow analysis, which is the subject of this lecture. We'll look at the basic definitions and methodology of material and energy flow accounting, in short MEFA. We look at what indicator elements are, proper units of measurements, indicator definition, and then a few practical examples. Material flow analysis is the systematic assessment of stocks and flows of materials within a system defined in space and time. That is the formal definition. And it means that we look at nature and look at industry and see where the materials flow, where they are stored, where energy flows and where it is stored, and then we try to systematically assess and account for these stocks and flows. We also need to know what a material is. In industrial ecology, material is an umbrella concept to comprise substances like chemical substances, oxygen or CO2, and goods like cars or cement or steel. All those are generally called material, and these material we want to account for and want to quantify. We do that by having an explicit system definition. We will draw a system boundary around those elements and stocks and flows that we want to study. This boundary contains processes, here shown as black boxes with numbers, and these processes are connected by flows from one process to the other process, or from outside the system to a process, from a process leaving the system. And these processes can contain stocks. And stocks can change, so we also need to account for the stock change. That is the very basic approach to accounting for material and energy flows and stocks in a system that we want to study. The system could be a nutrient cycle, it could be a product system, or an entire economy of which we want to quantify the total material throughput. The basic elements of the system boundary, system definition, were already presented, and here we have some formal definitions again that I pause now quickly so you can read them. We have the system boundary that tells you what's inside and outside. We have the processes, which are elements of the system where material energy is transformed or stored or distributed. We have the stocks, which are amounts of resources that are stored somewhere for a certain amount of time. And we have the flows that show us where material energy are transported from one process to the other over a certain time. Many industrial ecology models need quantitative approaches and need a mathematical model. To do that, we need to assign symbols, mathematical symbols, to the different system variables. The system variables are comprised of stocks, stock changes, and flows. In this example, we will quantify the stocks by symbol S, so we have S1 for the stock of process 1, S3 for the stock of material in process 3. We have the delta S, which denotes the stock change in a certain process. We have the flows, FO1 going from outside the system to process 1, so this is the flow on the very left of the system. We have a flow F23, which is the flow of material or energy going from process 2 to process 3. Next to having the stocks and flows in our system, we also need parameters. Parameters are variables and numbers that connect different system variables to each other. There's a few examples given. One example is the so-called transfer coefficient. Transfer coefficient is a number that tells you how big one flow is in terms of another flow, like as a ratio. For example, in the one equation here, we say that F23 is K times F12. So the flow from process 2 to process 3 is a certain fraction K of the flow F1 to 2. Good example is the new scrap rate in automotive production. So every time the automotive industry consumes steel, that would be F12, it generates a certain amount of fabrication scrap, F23, and that ratio is roughly 20%. So K would be 20%. The parameter K would be 20% in this case. Here you see an example of a correctly defined MEFA system which is not quantified yet. You have the different processes with numbers, you have the flows with numbers going from one process to the other process, we have stocks and stock changes which have symbols, and you have the system boundary with a certain material you want to study, in this case it's cadmium, you have a geographical scope, and you have a year, a time period for which the system is quantified. This picture shows you a quantified MEFA system from the book of Brunner and Rechberger. It is the metabolism of a certain area in Switzerland, and you can see the different processes, the landfill, the industries, and you also have a Sankey diagram so you can see where actually the flows are biggest. The indicator element in this case is the element lead. A core feature of material and energy flow analysis is the process and the system balance. Mass and energy balance is a fundamental law of nature, and in our assessment for industrial ecology we have to respect those balances so that our assessments are valid. We can establish the mass and energy balance equation if we look at each process in our system definition and quantify all the incoming flows, subtract all outgoing flows, and the result must be the net stock change. If we, for example, look at process 1, we have one incoming flow F01, another one F31, and the sum of those two here minus the flow that leaves the process 1, F12, must equal the stock change of this process 1. You can do this for every process in your system definition, and if you add the mass balance or energy balance equation for all your processes, you end up at the system energy or mass balance. In this case, it is F01 minus F20 minus F30, which is one incoming flow from the outside minus two outgoing flows. This difference must equal the total stock change in your system. So whatever comes in either leaves the system here or there, or it's accumulated within the system. For a fully quantified system, the number of system variables that you have must equal the number of balancing equations for each process, plus the number of parameters that you have, plus the number of measurements that you have to make in addition. And we will see that in several exercises how this principle applies so that you can quantify how much information you actually need to fully quantify your system. The reason why we have this relationship here is that each mass balance equation is a constraint for your system variables. If you look at the very simple case in process 2 has one incoming flow and two outgoing flows. If you know two of the flows, the third one is already determined by the mass balance. You can't change it anymore. And so each mass balance equation constrains the system variables so that the actual number of information that you need is reduced by 1. So the rest of the information can be either quantified by parameters, for example, the two flows always have a fixed ratio, or it actually has to be measured. And again, in the exercises, we will see how that works in practice. Right now, we will continue with a few examples for material and energy flow analysis. The first example refers to Sankey diagrams as a proper representation of the system that we analyze. The Sankey diagram is a system definition where the width of each flow is proportional to its value. So you can have Sankey diagrams for energy, that is the most common one, but you also can have Sankey diagrams for mass. So the only thing you have to do to get a Sankey diagram is you take the system approach that we just introduced and you choose the width of each flow between processes as proportional to its value. Good example is here, work from John Cullen in Cambridge, where you can see a snapshot of the global steel cycle with the primary production on the upper left side, the recycling on the lower left side, and then you can see how the mass flows of steel trickle into different products of steel, the different rolled and formed products, and how these on the right side finally are transformed into consumer goods. So just by looking at the flows, you know where in the system the big flows are and also to which processes they're connected to. The difference between this approach and the other one is that here processes are not shown as boxes, but as cross-section lines that transform one set of flows into another set of flows. There's a few common mistakes that you can make when you define MFA system, not only in material flow analysis, but of course also in all the other disciplines, especially in life cycle assessment. There's a few don'ts that are shown in the left drawing, and in the right drawing you can see how those don'ts can be fixed. I leave a few moments so that you can read this slide. One thing that we do not like in a systems analysis is when one flow branches into another flow. Because then it's hard to get the naming right, it's hard to establish mass balance equation that can be very quickly confusing. So if you have such a situation, please resolve it in the way that is shown here on the right side. You have one proper flow going from 1 to 2, and you have another proper flow going from 1 to 3. A stock change or a stock should always be embedded in a process so that we can say there's a stock in that process, to not confuse between stocks and processes. It's also a good advice to always have the material that you analyze, the time frame that your analysis for, and the regional scope explicit in your system definition so that at first glance everybody knows what you're talking about. There's a few smaller items that are also listed here, but the ones I just mentioned are the ones that are most important. In material flow analysis, we have the challenge of finding the right unit for the mass balance. If there's no nuclear reactions involved, the mass balance holds for the total mass and also for each chemical elements. So what we can do is, instead of quantifying the total mass, we only quantify the mass for a specific chemical element. This is often easier to do. You can imagine, for example, you're making an MFA for food, then you also have to quantify the water content of the food to get the balance right. This is maybe not necessary to get your message across, so what you could do if you choose to make a material flow analysis for food is to only quantify the system for the nutrients like phosphorus and nitrogen. You still can carry across the main message, but you don't have to do the work to do a full mass balance, including all the elements and all the other substances that you are maybe not interested in. So indicator elements are a way to reduce the information load of your system to just have the core information content and still satisfy the mass balance. Here are a few comments on the units of measurement in material and energy flow analysis that apply to industrial ecology as a whole. We have three types of quantities in our systems. We have flows, we have stock changes, and we have stocks. And for those we can quantify the mass or the energy and the quantity or monetary units. And since a flow is always measured as something flowing over a period of time, we always quantify a flow as the amount per time. So you can say, for example, the steel production of China in 2013 was maybe 1.1 gigatons per year, because it was during that year that this flow happened. The same with stock changes. Stock changes have the same unit as the flows. Something changes over a certain period of time. This is why a stock change and a flow is always measured as a rate. It's different with a stock. A stock is measured as a snapshot in a process at a certain time. For example, you can quantify the number of cars in your city where you live in at a given point, let's say now. And if you do that, you don't have a per time measurement, but you have a measurement at a certain time, which is this and that big. So the stock of a certain material is kilograms or megatons or gigatons at a certain point of time, but there's no extra time unit needed. You just say, I measure this stock at this time and its size was so and so many megatons, period. And the same applies to energy units, which could be terajoule, exajoule or gigajoule, kilowatt hours, or the quantities, which are items or monetary values. In industrial ecology, we often see the necessity to quantify the system that we analyze at different layers. For example, we need to quantify the energy layers because we want to study energy flows and energy efficiency improvements. At the same time, we want to quantify materials layer because the material are embedded into the products that we then consume. We also are interested in quantifying emissions because the emissions couple our system to environmental mechanisms like climate change. The good thing is that we can just do that. We can use a consistent system definition to quantify emissions, energy flows, material flows in stocks, the products, and maybe also the services that we enjoy from these products in a common framework. This is typically done in life cycle assessment, where we connect flows of different units, for example energy flows with water flows, to form products, so that we have always the right unit, the unit that we're most interested in quantified in our system. At the same time, we also keep track of other flows that we may need later. A good example is the flow of passenger vehicles that we record to understand how many people can use the cars and maybe to quantify how much energy we need to operate the cars. If we also keep track of the material content of the passenger cars, which is the materials layer, we can then, once the passenger cars leave the use phase, quantify how many materials we can recover from these cars. So this is what we do when we quantify the system at different levels. It is to keep track of the different quantities, material, energy, and emissions that are relevant at different stages of the life cycles of the products that we study. In quantitative systems analysis, we can explicitly define performance indicators. This is a crucial feature of the explicit approach. We can, in general terms, define indicators like efficiency as something like the useful output divided by the total input. But when we do this in colloquial language, we not often or not always can be explicit about what exactly is part of the useful output and what exactly is part of the total input. So what we can do is we can point to the system definition and exactly specify which flow is part of which indicators. For example, for process number 2, we can specify an indicator that is maybe the material efficiency of process 2, which is divided by the flow F20 divided by F10. Output divided by input. The difference here is that I don't do this in words, but instead is I point the reader of my work to the system and say, to obtain this indicator, I divided this flow by this flow. This is a very explicit method to define the indicators that you then use to assess your system. And we also have an exercise prepared in the online course that helps you understand the value of this way of defining indicators. This is the exercise IEooc Methods1 Exercise 1. When we now apply the concepts of material and energy flow accounting in practice, a typical image that you will often see, especially in material flow analysis, is the image of a material cycle that comprises all the steps of the life cycle of materials, from the mining stage to the fabrication and processing stage to the use phase and to the waste handling industries. And you have reuse flows, you have remanufacturing flows and recycling flows that then make an anthropogenic cycle of materials. And of course, this material cycle is not seen in isolation, but it is linked to the natural environment in form of the lithosphere and the hydrosphere, and also the atmosphere via the emissions from the different processes. Material flow analysis and energy flow analysis can be applied at any geographical and temporal scale and to any element or type of energy. We have in industrial ecology analysis at the city level. Here just a quick example, studying phosphorus flows in Beijing. We have it at the regional level. We just saw it for lead in a region in Switzerland. We have it at the national level, for example, for steel in China. We have it at the plant level, for example, energy flows in a paper mill, and also at the global level, for example, here the global material flow analysis of neodymium. So the approach is very general, very basic, at the same time very powerful. So I see this as one of the core methods of industrial ecology that helps you also better understand the complementary approaches like life cycle assessment and also input-output analysis. Material and energy flow analysis is also often applied at the economy-wide level, and this is called then economy-wide MEFA, or also material flow accounting. In this method, the whole economy is modeled as a single process, and you can quantify the total input to this economy, the total stock formation, and the total output. And you can, for example, define what we call resource efficiency of a national economy. That is defined as the total material input to that economy divided by the total economic output, which is the GDP. So this is one of the main resource efficiency indicators that is used alongside with just the GDP in many countries to see how much economies are dependent on material flows. This is one of the major applications of economy-wide MEFA. We can also use material and energy flow analysis to study the degree of circularity of national economies or of the global economy. What you see here is work from colleagues from Vienna quantifying the material flows into the economy and then the ones that are processed as energy carriers that go out. So these yellow ones are fossil fuels, the green ones are biomass, and those flows that are processed into materials or commodities that are then used as stocks, for example, vehicles or buildings. So here you can see these large orange flows. These are the construction materials. You can also see that compared to what is flowing in, much less is coming out, only 50%, because the stocks of buildings and infrastructure are still growing also in the EU. And then from what is coming out, maybe only half is actually recycled, so that in the end you can see that even a very mature economy like the EU27 are far from being something what we call today a circular economy. So probably there are some major improvements needed also here. The material and energy flow analysis approach is very basic and is also distinct from other approaches that we use in industrial ecology. The first distinct feature is that in MEFA and energy flow analysis we quantify the entire system for one or more materials. Not just parts of the system, but all processes and all flows are quantified for this material, and I can do the mass balance or energy balance for all processes in the system. The system quantification that we write down is valid or measured for a certain time period only. So we say we have measured flows in 2014, so our quantification of the system is valid for this 1 year only. And also we always have a regional scope, so we can say these quantifications apply to this certain country or this certain regions. And we always enforce the mass balance or energy balance on all processes within the system. If you compare this to LCA, for example, points 1 and 3 do not necessarily hold. In LCA we also use systems, but we don't quantify the entire system for one material. Instead we measure each flow that we're interested in the most natural unit of measurement. So for example, a passenger car we would measure in terms of items, so how many passenger cars, but we would not measure its steel content. The steel flows we would measure in kilograms of steel, but not of their energy content, and electricity we would measure in terms of energy, of course. So we also have explicit systems in LCA, especially in process-based LCA, but these systems are not quantified in the same measurement unit or for the same material all over the place. Instead, each flow has its own specific quantification. And as this is the case, we can also not establish the mass balance or the energy balance in most LCA systems because each flow has a specific unit of measurement. So this is a major difference between the two approaches. As a last slide, I want to point you to the STAN software for material flow and energy analysis, which is a basic free software to help you define systems, quantify flows, and make some basic mass balance check, and also to reconcile your data. So if you're working with basic material energy flow accounting, this is definitely a useful tool. And with this remark, I want to thank you for this attention and close the lecture.